Good morning, guys. Can you hear me? Can you wave your hand? Yeah? Okay. Sounds good. So, where are we in this class? We just finished chapter 1. Let me share my screen. Share my screen. And this is our syllabus. So we finished chapter 1, the foundations of biochemistry, on Wednesday. You had a homework due this morning, right? So hopefully you got that done. It wasn't too difficult, was it? No? And so today we're starting a new chapter, chapter 2. We're going to talk about water. Oh, wait. Yeah, no, that's correct. So we have 2 lectures on water. You may wonder, what is it about water, right? That requires 2 lectures. Well, you'll be surprised. Water is a molecule that you can study and study for forever and still not fully understand what that molecule is capable of and what its properties are. Okay, so let's go to our slides. So салфетки принеси. Okay, so as the slides are uploaded to Canvas, so you can always download them. And of course, you can take notes as we go through them. Now, I don't know what's easier for you. Maybe handwritten notes, maybe easier in this kind of format. Because it's probably going to be hard for you to listen to a Zoom presentation and at the same time take notes by typing something. So I leave it to you to figure it out. I would probably just take handwritten notes. Sorry. Okay. So just as I mentioned at the beginning of each chapter, we're going to outline our learning goals, right? And this is what we focus on when we study. This is what we focus on when we prepare for the tests. So life occurs in water, right? So what kind of interactions occur between molecules in water, right? And why is water a good medium for life, right? So what is it about water that makes living organisms thrive in water? So there will be polar molecules, and obviously there are also non-polar molecules. Very important part of it, and the fact that non-polar molecules aggregate in water is also important because that's what will make vesicles, that's what will make vacuoles, that's what will make biological membranes. So even though something that is not soluble in water plays a huge role by being in water, okay? Because water will shape its properties. Okay, but there's also it's a two-way street, and we'll talk about how dissolved molecules alter properties of water. Right? What happens to water when you dissolve molecules in it? So we'll talk about the weak acids and weak bases, right? So here we'll talk about buffers and why we need them, right? So remember, buffers is something that allows you to maintain pH at a reasonably constant number. And finally, how water participates in biochemical reactions, right? So water is not just a medium, but also is a reactant. So it enters chemical reactions with other substances. Now, as I mentioned to you guys, please always stop me, always ask me questions. Now, I don't see the chat. There must be. What if I switch to this? Oh, there we go. Pause participants, stop security, pollen, annotate remote. Oh, there is chat. I lost it for a while. Yeah, so if you are too shy to unmute your microphone, you can type something in the chat. I will not get to it right away, but I will be checking chat once in a while to see if there's anything there that is worth addressing, okay? Right, any questions about the learning goals? So here's what we need to focus on as we go through this chapter. And it will be today, and it will be on Monday. Okay. All right, so I'm going to start by stating that life evolved in water primarily due to its ability to protect from UV light, right? So water absorbs the UV light and protects living organisms. And then in general, we are made of water, right? So 70 to 90% of living organisms are made of water. So chemical reactions. So think of water as a very polar compound substance, right? And remember, polar substances, polar solvents accelerate chemical reactions, right? Like they accelerate chemical reactions because they stabilize transition states. Remember, transition states in most cases are polar. They involve formation and breaking of bonds, which means charges, and water will stabilize those charges. And of course, also the interaction of macromolecules such as proteins, nucleic acids, and biological membranes with water will determine their tertiary structure. Now, as far as water, let's quickly look at the molecule here. Now, remember that you will not draw water this way, right? It's not a linear molecule. The reason why it's not a linear molecule is because of these lone pairs of electrons, right? Lone pairs of electrons, it's a tetrahedral. Go back to this slide. So because of the octet rule, so there are 4 electron pairs around an oxygen atom in water, and they are formed by sp3 orbitals. So 2 of these will covalently link hydrogen atoms, and 2 remaining ones will be non-bonding pairs, right? So here we have hydrogen atoms, and here we have non-bonding pairs. And so the water molecule, the proper way to draw it would be a bent shape, right? Bent shape. And here you will draw something like that. right? Two non-bonding orbitals. So sp3 hybridized tetrahedron. What else is here? Distorted tetrahedron. Okay, question for you. Why is it distorted? Why is it not a perfect tetrahedron? Anybody knows? Anybody knows why is it distorted?
Because the lone pair of electrons.
Right, so lone pair of electrons. And why do they make the tetrahedron distorted?
They repel the other things away from it.
Yeah, so if you look at this, let's go back to the structure of water. Why am I struggling? Here. Now, so these electrons here, which are between oxygen and hydrogen, they're kind of confined into this space, right? So they kind of squash between oxygen and hydrogen when they form this sigma bond. These electrons, they're only attached to oxygen, right? There's nothing on the other side, which makes them much more diffuse, makes them bigger, right? And so if it makes them bigger, then these electrons need more space than these electrons. And because of that, so these two hydrogens will actually be kind of squashed a little bit, right? So this will be a distorted tetrahedron. And so there will be a dipole moment, which makes sense, right? So oxygen atom is more electronegative. And because of the dipole moment, water can serve as both hydrogen donor and acceptor. All right, so in addition to being a strong dipole, water is capable of forming what's known as hydrogen bonds, right? So in general chemistry, organic chemistry, you learned about hydrogen bonds, and which we did not give you a precise definition of hydrogen bonds because still nowadays people still don't very well understand the nature of hydrogen bonds. So on the one hand, they are partially bonds, just like regular bonds. On the other hand, they're just interaction between dipoles. So it's kind of in between. And usually you need two electronegative atoms, nitrogen and oxygen. And so ideally you will have three atoms involved in a line. So let's look at that. So, so here we have a strong hydrogen bond. So, so this is an alcohol. The hydrogen is attached to this oxygen. So this will be some kind of phosphate. We will learn more about phosphates later. And you can see here, one electronegative element, another electronegative element, and the hydrogen is stuck in between, right? Now, keep in mind that it has to be an electronegative element, no carbon, right? So if you have a carbon-hydrogen bond, forget about hydrogen bonds. No hydrogen bond when you have a CH, okay? And generally, these hydrogen bonds are stronger when they're linear rather than when they're bent. Now, there are reasons for that. It's treated at much more deeper level of theory, so which is beyond our class. But whenever you look at the biological macromolecule and look at the hydrogen bond involved, if you see a linear hydrogen bond, then take note that it's going to be a stronger hydrogen bond than when it is bent.
I have a quick question.
Yeah.
So would the weak hydrogen bond as a bent molecule be the reason why water easily dissociates when it comes to being mixed with stuff? That makes sense.
why water easily dissociates.
Is that due to the fact that it has weak hydrogen bonds because it's a bent molecule?
Ah, wow.
Like I know hydrogen readily pairs with, let's say, an acid that goes in water, something like that. I think.
Yeah, but okay, let's see. So let's say, but you say you have a bent water, but you can still form a linear hydrogen bond even though it is bent. Right? Like that. So even though the water molecule is bent, but the hydrogen bond shown here is linear, right? So, but in general, we will see a little later in this lecture, or maybe on Monday, that water actually doesn't easily dissociate, right? So the equilibrium for neutral water versus protons and hydroxide ions is shifted largely toward the neutral water molecule. So yeah, I think this has, I don't know if there are, I'm sure, I mean, there's so many hydrogen bonds going on within a glass of water, right? So I'm sure the geometry of hydrogen bonding is important there. But I think for our purposes, it's more about how hydrogen bonds form between and within macromolecules, proteins, DNA, right? So we will see that in DNA, the hydrogen bonds are all linear. Not all, but the strongest ones are linear, which are responsible for the complementary base pairing. Okay?
Okay, thank you.
Mm-hmm. All right. So let's continue talking about hydrogen bonding in the water. So water can be hydrogen bond donor and hydrogen bond acceptor, just like what we drew here, right? So this, now where? How did I get the, still need to learn the tools. Annotate. I guess mouse. Yeah, I don't know. Anyway, so this part of the of this hydrogen bond, so this molecule of water is a hydrogen bond acceptor, right? Basically, it accepts a hydrogen. Now, this part is a hydrogen bond donor because this oxygen donates this hydrogen towards the hydrogen bond, right? And so because water has both oxygens and hydrogens, it serves both as a hydrogen bond donor and hydrogen bond acceptor. So because of this hydrogen bonding, the water molecule gives us a very high boiling point, right? So remember, boiling point of water is 100 degrees Celsius. So if you think about other molecules about the same weight, they boil at much lower temperature, right? So for example, methane, right, which has about the same molecular weight, is a gas at room temperature and atmospheric pressure, right? So it boils at extremely low temperatures. And the same for melting point, right? So so water will so form ice, obviously, right? Which will freeze at 0 degrees Celsius. Unusually large surface tension, right? So if you spill water on a flat surface, remember, it will not be just a flat puddle. On the edges, it will be curved, right? And the reason why it will be curved is because water molecules will attract each other and pull themselves to one another and form a curve. So that results in a surface tension. Or remember, like if you have a test tube, like so, and you pour some water in there, it will look like this. Right? So these molecules on the edges, they will pull other molecules towards each other and result in a curve. So that will give you a surface tension. And that's because of the hydrogen bonding, right? So the water molecules attract each other. Now, hydrogen bonding in water is cooperative. Now, do I have a slide on cooperative? Let's see. No, I don't have a slide on cooperative. So if remember what cooperative means. So if you have molecule of water this will form a hydrogen bond with another molecule of water. What will happen? So if this hydrogen is pulled away from this oxygen, then this oxygen will develop partial positive charge, right? So sorry, partial negative charge, delta negative, and it will pull a hydrogen from another molecule of water, like so. So that's what's meant under cooperative, right? So one hydrogen bond here causes another strong hydrogen bond here, and then so on and so forth, right? So they all talking to each other. All hydrogen bonds talk to each other. Okay. But keep in mind, so these are not covalent bonds, right? And they're still much weaker than covalent bonds. Just some numbers, 20 kilojoules per mole compared to 420 kilojoules per mole for covalent bond. And so because of that, remember the bond strength is also reflected in bond length, right? So in a covalent bond, we have about 0.096 nanometers distance between oxygen and hydrogen. In the hydrogen bond, it's about 0.17 nanometers, right? And here's the angle. I just couldn't remember it at the time, but remember when I told you about distorted tetrahedron? So in a perfect tetrahedron, this would have been what? What's the angle that would be here if the tetrahedron was perfect? Anybody remember? 109. 109, right?
109.5, yeah.
Yeah, 109.5. But because of we have this huge ears, right, of non-bonding electrons, because they're bigger than these, then this space is bigger than the space between oxygen and hydrogen, they will push these two hydrogens toward each other and make this angle slightly smaller. So distorted tetrahedron. All right. All right. Importance of hydrogen bonds. Well, they're just everywhere. Sources of unique properties of water. We just talked about that. Structure and function of proteins. We'll see that proteins with will form lots of hydrogen bonds with each other and also with water around them. DNA strands will hold each other or will be held close to each other to form complementary bonds using hydrogen bonding. Polysaccharides, we'll see that's everywhere, right? So we'll see polysaccharides, for example, a starch or cellulose, all these polysaccharides, the reason for their properties is hydrogen bonding. Substrates to enzymes, right? So, so enzymes, remember, catalyze chemical reactions. And so many substrates, small molecules bind to the enzymes through hydrogen bonding. Hormones to the receptors, matching of messenger RNA and transfer RNA. And so Linus Pauling, one of the probably biggest chemists ever, who won 2 Nobel Prizes. Very rare when one person wins 2 Nobel Prizes. And and so he really believed that in the structural chemistry, when you apply that to physiological problems, you will find that hydrogen bond for physiology is greater than any other structural feature. Well, life occurs in water, right? And water's main property is hydrogen bond. So dissolve alcohol in water. There's a hydrogen bond. What's a good example of this situation? When you dissolve alcohol in water. Can you think of a keyword I'm looking for here? Starts with a V. Nobody remembers? All right. So you buy that at the liquor store, right? It's vodka. So when you dissolve ethanol in water, so when you look at the bottle, you will see there's only one layer, right? So which basically means that ethanol is fully miscible with water. And the reason for that is the hydrogen bonding, right? So I can see ketones have lone pairs, form hydrogen bonding with water. Now it's different peptide chains. So we have amide bonds. And here's we have a component of DNA, right? So there are two hydrogen bonding in DNA, and that's what I was telling you about the linear arrangement of these hydrogen bonds. So nucleic base thymine binds to nucleic base adenine through two hydrogen bonds, like so. So complementary basis of DNA. All right, so ice in a crystalline form. The reason why ice has such a beautiful crystalline structure is because of these beautiful hydrogen bonds. So it's hexagonal. And as you remember, ice has lower density, right? Ice has lower density. So in other words, there are fewer molecules of water per cubic meter of space, right? Lower density. And what's the experimental confirmation that ice has lower density?
Ice floats.
It floats. It floats. Ice floats. The ice floats, which means that it has lower density. All right. So water will be a good solvent because of its hydrogen bonding and dipole. Will be a good solvent for charged and polar substances, amino acid peptides, small alcohols, carbohydrates, but will be a poor solvent for non-polar substances, aromatic molecules, aliphatic chains, non-polar gases. You know that if you spill gas at a gas station, it will not go into nearest water puddle in the rain, for example. It will stick to its own, and you will have an ugly spill at the gas station because gasoline will not dissolve in water. So in general, we can see here in blue, right? So these are functional groups in molecules, which will make them dissolve in water, right? So you can see here lots of OHs capable of hydrogen bonding, lots of charges, like for example the amino group, which is protonated, right? And carboxylic group, which is deprotonated, so negatively charged, positively charged, doubly negatively charged. So these amino acids. Lactate, which is another important physiological acid. So it has both. It has a charge and it has a hydroxyl group capable of hydrogen bonding. Glycerol, important biological molecule as well. On the other hand, so these are lipids, right? So you can see here when you have long carbohydrates, or not long hydrocarbon chains. So non-polar, total non-polar. So this will not dissolve in water. Now, but then there are also amphipathic molecules, which have both, right? So for example, amino acid phenylalanine, it has both. It has an aromatic ring, which will make it repel water. It will not want to go in the water, but the charged portions will go into the water. And when you have a slightly bigger molecule like this, where the hydrocarbon long chains and this tail here, which is charged, two charges, right? Lots of polar residues. Then molecules like this will be the basis for biological membranes. And we will look at those structures later in this course, right? So these are amphipathic molecules, which will form specific aggregates in water responsible for biological properties of the cell, for example, cell membrane. All right. So what do we remember from general chemistry? We remember ionic interactions, right, between charges. Very simple. Dipole, we just talked about in water. Van der Waals interactions. So these are interactions between nonpolar groups. So for example, in lipids, right? So if you have a large surface area, you will, even though the molecules are not polar, you will still develop these van der Waals interactions. And remember, this is known as what's induced dipole. So if you don't remember this, the term induced dipole, please look it up in your organic chemistry text or general chemistry text, or just Google it. And it will give you the definition of the van der Waals interactions and induced dipole, right? And so generally at a reasonable distance, so these will be attractive, but if you push them too close, they will become repulsive, right? So the electrons in these bonds will hate each other, and you will create something which is known as steric hindrance. Steric hindrance. So in organic chemistry, this is one of the key terms. Steric hindrance. When the groups of molecules come too close to each other, the electrons will start hating each other, will repel each other, and that will result in steric hindrance. And hydrophobic effect. Okay, hydrophobic effect is very interesting. So for when I actually started studying chemistry, I thought hydrophobic effect meant that hydrophobic substances attract each other. But it turns out that's not so, okay? So hydrophobic means something that hates water. Phobia, right? And hydro. So something that is phobic towards water. So I thought that these substances, the reason why that is so is because they attract each other. But that's not always the case. So let's look at the, let me skip a couple of slides. And we'll come back to these slides. Yeah, let's look at about hydrophobic effect in a little more detail. And then we'll go back to the couple slides that we just skipped. So, so it turns out so many nonpolar molecules associate in aqueous solutions. And the hydrophobic effect is actually extremely important because, for example, it's responsible for protein folding, right? So proteins adopt three-dimensional structures in water because of hydrophobic effect. Many proteins interact with each other through hydrophobic effect. Lipid micelles, okay, so here we talked about, for example, soap, formation of soap, bubbles in water. Binding steroids to hormones to their receptors. And so the key here is that it does not arise because of some attractive effect between the two nonpolar molecules. It has a different nature here. So so when you have molecules of water just by themselves, right, with no solutes in water, so these molecules of water, they jump all over the place, they move around as much as they want. Some hydrogen bond breaks, other hydrogen bonds form. So very high entropy, lots of disorder. And remember, so the key equation here, so what we're looking for is low energy. right? So if you have high entropy, high delta S component, then so this unit here, T times delta S, because this has a negative sign and positive high entropy, then delta G will be highly negative. And so whichever process that results in this high entropy will be favorable, right? Remember, any favorable spontaneous process is accompanied by very low delta G, negative delta G. Now, what happens if you put a molecule in water which has a long hydrophobic head group? So you can see here, to accommodate for that, the water molecules, like soldiers, basically arrange themselves or order themselves around a hydrophobic substance, kind of create a pocket for it, right? Which will result in what? Will result in highly arranged molecules, highly ordered molecules, and low entropy, right? So these molecules are stuck. They can't really move as much as they want. They can't jump all over the place. Hydrogen bonds don't form and break easily. And so the result is low entropy, right? So this is thermodynamically unfavorable, and hydrophobic solutes have low solubility. And to compensate for that, so now let's say you have these lipids in water, right? So you throw a bunch of these molecules in water, and this water orders around here, it orders itself around here, it orders itself around here, and so basically the result is extremely low entropy in the process, unfavorable state. So each lipid, molecular forces surrounding water become highly ordered. And to compensate for that, what happens is that these lipids start to aggregate, right? They come close to each other, and you can see here now compare this situation where each lipid is surrounded by water molecules with this situation where basically these lipids aggregate, and then you only have these molecules of water which surround them, right? And all the other ones are freed up. So obviously this is a favorable process, right? And it will push these hydrophobic chains together, resulting in a slightly higher entropy, because fewer molecules of water surround this aggregation. And so this is sort of the nature of the hydrophobic effect. It will basically push the hydrophobic chains together to free up the molecules of water and increase the entropy. Does it make sense? Anybody has any question about that? Let's see if there's something in the chat. Yeah, molecules are shown the same. Yeah, just to go quickly back, for hydrogen bond, just always try to draw a linear one. If geometrically it's impossible, it will be bent. So basically the linear one is always preferred. Okay.
Just a question, real quick to clarify. So the hydrophobic effect is essentially why the cell membrane forms its shape.
Same thing, right? So the lipids in the cell membrane. So in fact, this is a miniature representation of cell membrane, right? So instead of this situation where you have lipids all over the place, they will aggregate and line up like this to form a three-dimensional structure where the entropy is not decreased by so much because the water molecules are released. Yeah. So.
Okay, thank you.
Yeah. All right, so what did we skip here? Well, we talked about the entropy hydrophobic effects, steric hindrance, examples of non-covalent interactions. Let's see how much time we have left. We have a few minutes. Peptide bonds. So we have ionic interaction, repulsion between positive charges, attraction between opposite charges. Now here's the hydrophobic interactions. Here's another example. You have a hydrophobic group here. You have a hydrophobic group here, and they tend to associate close to one another. Again, not because they are attracted physically to each other, but rather because they allow for more molecules of water to be released in the environment, which will result in an increase of the entropy. But obviously we know that polar substances or ionic substances fully dissolve in water. And so, for example, this is the solution of sodium chloride. So, so you can see this is the crystal of sodium chloride. It's pretty strong, right? Because of the ionic interaction between sodium and chloride. But it's replaced by ion dipole interaction. So you can see here the chloride will be ripped apart, ripped away from this crystal because of all these hydrogen in water, all these hydrogen atoms, which are partially positively charged, will be attracted to it through electrostatic interaction. And sodium ions will be taken away from the crystal through the electrostatic interaction with the oxygen atoms. Okay. So for van der Waals, when you Google van der Waals, when you look at the induced dipole, for example, one of the great examples of such a van der Waals interaction is binding of a drug into a protein pocket, right? So if you have a drug and it binds to something in the body, so the van der Waals interaction will be responsible for this drug to occupy this pocket, and also hydrophobic effect, right? So you so if this drug is, let's say, hydrophobic, and there are all these molecules of water that are organized and ordered around it, which is known as hydration sphere. So when the drug comes in, when it binds into the pocket, all these molecules of water will be released, right? Which will result in the increased entropy. And the drug will stick to the pocket and stay there and perform its function. But obviously, the drug has to be sterically complementary to the pocket. So which is known as lock and key complementarity. So your drug is a lock, your drug is the key, and your protein is the lock, right? So if the key fits into the lock, then the drug will go inside, release the water molecules, which will result in increased entropy, and the drug will occupy the pocket and perform its function. All right, so let's see where we are. Notation, sure, we'll keep the notations. We are about halfway, slightly less, halfway into the lecture. So as usual, I will post this Zoom presentation on YouTube, right? And I'll send you the link. And we'll have one more lecture on chapter 2. And before we close, are there any questions that I can answer at this point? But guys, please put more questions, put more comments into the discussion sections of the Canvas, right? So take advantage of that and learn from each other, and I'll help you with that as well. So. Okay. No other questions? All right. Well, have good weekend, guys. Study and stay safe. All right.
Thank you.
Yeah,
You too.
bye.
Have a
Thank
good
you.
weekend.
Bye.